Post-irradiation examination. Post-irradiation examination (PIE) is the study of used nuclear materials such as nuclear fuel. It has several purposes. It is known that by examination of used fuel that the failure modes which occur during normal use and the manner in which the fuel will behave during an accident can be studied. In addition, information is gained which enables the users of fuel to assure themselves of its quality, and it also assists in the development of new fuels. After major accidents, the core, or what is left of it, is normally subject to PIE in order to find out what happened. One site where PIE is done is the ITU, which is the EU Center for the Study of Highly Radioactive Materials. Materials in a high radiation environment, such as a reactor, can undergo unique behaviors such as swelling and non-thermal creep. If there are nuclear reactions within the material, such as what happens in the fuel, the stoichiometry will also change slowly over time. These behaviors can lead to new material properties, cracking and fission gas release. Fission gas release. As the fuel is degraded or heated, the more volatile fission products which are trapped within the uranium dioxide may become free. Fuel cracking. As the fuel expands on heating, the core of the pellet expands more than the rim, which may lead to cracking. Because of the thermal stress thus formed, the fuel cracks. The cracks tend to go from the center to the edge in a star-shaped pattern. In order to better understand and control these changes in materials, these behaviors are studied. 1234. Due to the intensely radioactive nature of the used fuel, this is done in a hot cell. A combination of non-destructive and destructive methods of PIE are common. In addition to the effects of radiation and the fission products on materials, scientists also need to consider the temperature of materials in a reactor, and in particular, the fuel. Too high fuel temperatures can compromise the fuel, and therefore it is important to control the temperature in order to control the fission chain reaction. The temperature of the fuel varies as a function of the distance from the center to the rim. At distance x from the center, the temperature Tx is described by the equation, where R is the power density Wm3 and Kf is the thermal conductivity. Tx equals T rim plus R pelletwo x2 4 Kf1. To explain this, for a series of fuel pellets being used with a rim temperature of 200 deg C, typical for a BWR with different diameters, and power densities of 250 Wm3 have been modeled using the above equation. Note that these fuel pellets are rather large. It is normal to use oxide pellets which are about 10 mm in diameter.